Hello, hello, Professor Cruz.
Hello. Good morning, Professor Santilli. How are you?
Fine, very nice. Can you can hear me normally? Yes.
Yes, I can hear you. Okay. Yes.
Please say hello to Professor Hilda.
Okay. When I see she, I say, of course. Good morning, Professor Will. Yes.
Well, thank you.
Good morning.
Good morning.
Good morning, Dr. Pace. Nice to see you.
Yes, I'm glad you were able to find the link to the meeting, Dr. Santilli.
Thanks to your courtesy, because you sent it back to me, and I looked everywhere, but must have been trashed by the. Where I have this new Mac. It's too many features. It's sometimes they're overwhelming.
Yes.
May I ask you, where are you physically now?
Where am I physically?
Yeah, physically. Which city? Which country?
I'm in Canada.
Oh, in Canada. Okay, yes.
Near a city called Kingston.
Oh, okay. I know Kingston. Yes, indeed. In Canada
Yes.
was just enough for me. Just an idea of where you are, so I can physically locate in my imagination.
Yeah, no problem.
Good morning, everybody.
Oh, good morning, Dr.
Good morning, Professor.
Good morning, Professor Garrett. Good morning. Nice to see you.
You too, except I don't see you. Your picture is blocked.
Oh, I see. Let me call. Can everybody else doesn't see me? Just a moment, then.
Yeah, I only see just
Okay.
the name.
Yeah, what's planned for today? I didn't really understand. Who's talking today? Is Professor Santilli?
Yes. Santilli, Dr. Santilli is speaking about.
Just one moment. I'm calling. I'm sorry. Go ahead. I'm sorry.
It's okay. About isomathematics in general, isomathematics. I think in isocalculus in particular. I hope.
Oh, perfect.
Yeah. Carlo, they cannot see me. They only see my name. Could you please
Hello. I think the video here is blocked.
This may be the.
Yeah, here it is.
Okay, very well.
Are.
Okay.
Thank you. Carla, come here and see. Check one final additional here.
Yeah, I think it's okay.
Very well.
All right.
Okay, good enough. Sorry for the but Carla says hello to everybody.
Yes. We could perhaps wait a few more minutes, just in case we get any more participants. I will start, I guess, in the usual way, just reviewing our very short agenda. Let's see, share that. Yeah, so far on our agenda, we agreed last week that there would be no meeting next week, that is on November 10th. And the isocalculus had offered to give a presentation the week after that on November 17th. We still have openings for future meetings, so proposals would be very welcome. I added my own particular proposal, so based in part on discussions with Garrett during Professor Sovchik's presentation. I asked a particular question about the definition of geometry, and we didn't really get a chance to get into that. But I think it's fairly critical to the approach that Professor Sobczak has taken.
Okay, so it's settled then. You'll talk the week after Jesus, then I would suppose.
Yes, at least that's tentatively. If there's interest, then I think I would try to speak specifically about that one issue. Although there are a lot of things connected to it, but I think it was also, of course, a subject that was very important to Boschevich. I mean, he had very particular views about it, and for the most part, I think I've adopted his views. So, so I'll be trying to do that properly. The only other thing I was going to mention is that during this last week, I finally took the time to learn more about YouTube and what its benefits might be. I've sort of had difficulty deciding on the best way to store recordings, and so I've tried several different methods, but now I'm convinced that YouTube definitely provides us with the best options. So,
what options did you have? I don't understand. Yeah, I was surprised
well,
that
sorry?
you went to YouTube, but thank you very much.
Yeah, as long as you if you have any objections at all, like to having recordings there, please let me know. Right now, these recordings are not listed, except for my own. They are associated with what's called a YouTube channel, and people can subscribe to that channel, which would mean that they would automatically get notices when new videos are added to that group of videos. So all of these,
or you have to pay for that. No, I guess it's
no,
free.
that's free. It's a free service. It's been around for a long time. YouTube is probably the oldest service of that kind, and it just happened that I never really became familiar with how one actually.
It is owned by Microsoft now, I think.
In fact, I have one channel in YouTube, and it is very easy to actualize videos there. And then the only required is that all the people that is in the video be have one agreement of being in that video. And I think that in the seminar there, we have not problem with that. And the other is that we either use in the image only material that have not problem with the yes, with the authors.
Yes.
And that's free also? Do you have to pay for that?
No, it's free. It's free. It's free. Yes.
And there's no limitations on the total amount of storage, which is
no,
which is both surprising and convenient.
No, because the idea in YouTube is that if more people can see the videos, then it is used for publicity and something like that.
Yeah, then
there is no problem with payment of the service.
Okay, well that's great. So if there is no objections, then at least I should perhaps check with Greg as co-san, but in other words, I would just make these visible. Right now, the only presentation that's visible on that channel is the one that I gave, but I can make the other ones visible easily just by clicking one option. But even when they're not visible, they are still accessible if you know the link. So given this email with these links here, you can view the video. It's available. It's just not advertised on the YouTube site. And okay, so I found several convenient ways to get things there, as Jesus said. So what else? I think that's about all I wanted to say, and I would introduce our main speaker, Dr. Santilli. You're planning, I think, on continuing your presentation of isomathematics and isocalculus in particular. I look forward to that. I'll just stop my screen share and you can carry on.
Very well. Well, thank you. I'm sorry. I would like to thank, of course, Dr. Page, as well as all participants for this opportunity of exchanging potentially new ideas. It's exciting and it's appreciated. Very well. I am in the past lecture, I was supposed to give you an overview of a rather considerable number of notions that encompasses, what we call isomathematics. That was a very difficult task to do in 45, 50 minutes. So I elected a very rudimentary conceptual overview. This lecture is different, however. In this lecture, we have to deal with a specific topic, iso-differential calculus. So therefore, we have to be accurate, especially in the definition, and which I will try to do it. I should mention that in the past lecture, just for the record, I was a victim of a very very severe conjunctivitis following the second coronavirus. I never had it in all my life, but this is over now. So I'm back to my normal eyesight, which is the eyesight. It's kind of tired because of writing too much and working too hard for too many years. In conclusion, I will appreciate help in checking that all equations indeed are correct. Dr. Garrett, you have a very sharp eyesight. If you see any error, please let me know. I will say thank you, of course. Very well. So with this introduction, let me share the screen and perhaps let's get started. And one section, please. I believe this is it.
Yes, that's good.
Very well. Okay, now let me activate. Can you see my PowerPoint?
No.
Right now we see only your Zoom screen.
We are seeing your navigators because you select only share this window, this application.
So what do I have to select now? Let me call my wife.
Interrupt. You have a Mac. That's right.
Yes.
Yes. Interrupt your presentation and then go again to the green button.
Okay, which is the green button will be this one here.
Yes, and share screen.
Share screen.
Share screen, which is this one.
Yeah, press that one.
Yes, and then press this one. Okay, and then this one.
Yes.
Okay, now we are.
Yeah, it's all okay
yes,
now.
very well, excellent.
That looks perfect.
Very well. Well, with your approval, my plan is essentially the following. I would like to introduce the absolute minimum number of definitions that we need to reasonably minimum number that we need to discuss the iso-differential calculus, which is the main objective of our meeting. And during this presentation, I will appreciate, first of all, verifying that everything is correct. Any question, of course, is welcome. but discussion, I would like to appreciate if discussion can be deferred at the end of the conference, because at that time we can better discuss them better after the iso-differential calculus. So let's get
just to ask a question
please.
about the sequence. How much time would you prefer to have at the end for discussion? Just so that I can give you advice about remaining time.
My plan is essentially this introductory part about 15 minutes, then to discuss 15 minutes on the application, the meaning of them. Well, 15 minutes introductory on the definition, 15 minutes on iso-differential calculus, 15 minutes, very important, show the necessity for our needs and for especially for application. That's 45 minutes. And then essentially, but I can squeeze it, with less if necessary.
Oh, and I think we have an hour and a half, although we're starting a little bit late. So, but that's okay then. If you can finish in that time, we should have lots of time to discuss.
Yes, I would like to have all discussion during the presentation of the iso-differential calculus, but the beginning, the question, yes, but discussion, as we said before, later on. Very well. So let's get started with reviewing the foundation of isomathematics and therefore of isomechanics from the preceding very informal outline. And the basic notion, as we indicated, is the universal enveloping iso-associative algebra that is based on the now familiar iso product, which is characterized by the sandwiching of a new quantity, an operator in general, we call isotopic element, in between the product of any two quantities that have to be multiplied, with no known exception, no exception that I know, numbers, function, operator, etc. This isotopic element is solely restricted by the condition of being positive definite, but possesses otherwise an arbitrary functional dependence on any needed variable. This is a fundamental important point for this lecture, because iso-differential calculus, as you will see, is primarily intended to represent the totality of Newtonian forces, and most of them depend on the velocity. So not only you have coordinate of velocity, but you have pressure, temperature, wave function, etc., etc. The completion, the lifting, the isotopy of the product imply a corresponding compatible isotopy lifting of the multiplicative unit, which we denote with I hat, which has to be the inverse of the isotopic element, on which condition the iso unit verifies the axiom indeed of right and left multiplicative unit. Next fundamental quantity, also reviewed in the preceding lecture, is the isotopy Poincaré-Birkowitz theorem, discussed in details in my second volume with Springer-Belag. It's an infinite basis, as we all know, with the difference that there is iso unit and there are order isomonomial. Next, I recommend to have concrete examples for the isotopic element, specifically for discussing the iso-differential calculus. So we have something concrete. Here I present physical application, because from a mathematical viewpoint, there is no end in example of the isotopic element. I have to recall at this time a very important, very sound question by Dr. Garrett, namely, Ruggero, show me please the simplest possible example. I lost the balance, because it's not easy to locate a very simple example. But what I would like to bring to your attention is this simplest possible realization in physics, actually in chemistry in this case, of the isotopic element is essentially given by a conventional exponential exponential of a negatively defined quantity, large quantity in the numerator, so as that the value, numerical value of the isotopic element is infinite, it's very, very small. Sorry. Sorry for the interruption. So what do we see in the exponent? First of all, we see wave functions. Now, that's important for us because we want to represent nonlinear interaction by interaction, nonlinear in the wave function. And then we see a volume integral that is also important to represent non-local, our type of non-local interactions. That is also important to see that that whenever the EPR entanglement of particles is that we consider is ignorable, then this volume integral becomes zero, and the totality what I have to say recollapses into conventional applied mathematics and conventional quantum mechanics with uniquely and without any ambiguity. I should say in particular that everybody I have to say, which is specifically dedicated to the representation of protons and neutrons, you should think that everything I have to say is applicable, in our view, within a mutual distance of 1 FM, 10 to minus 13 centimeters. Beyond that's the dimension, then I believe the point-like approximation of particles is excellent, and therefore I do not see any need of EPR completion in that range. In other words, for isolated particle in vacuum, I believe quantum mechanics is absolutely perfect and there's no need for any change. However, I do see needs to change in what is called the interior problem, because we cannot simply reduce the entire universe to isolated point in empty space. Incidentally, this simplest possible realization of the isotopic element has been used for the proof of the last statement of the Einstein-Podolsky-Rosen, namely, quote, the wave function of quantum mechanics and IR of quantum chemistry cannot represent all elements of reality. End of quote. And indeed, there is an incontrovertible evidence of the meaning and the power of the intuition, the Einstein intuition, as well as by Podolsky and Rosen, that it is the case of the valence bond. Ladies and gentlemen, I worked for years on this problem, and I bank my name on the fact that it's impossible for quantum chemistry to represent the elements of reality of molecular structure in which the bond is created by identical electrons bonded together, entangled together at a very short distance. If you do the high school calculations of the force in between those two electrons, it becomes astronomical for particle standard, because it becomes of the order of newtons, which is a macroscopic measurement. So here you can see the germs of the solution. Here you see two different wave functions. The use of us, we can see, if you are interested, the technique essentially switched the wave function of quantum mechanics cases that only admits potential forces into a wave function that admits also contact interaction, and is the wave function of a strongly attractive Halton potential. That the emerging new strong valence bond, we use it to represent, for what I know, the only numerically exact representation of the hydrogen and the water molecule, but that's not enough. What is maybe most intriguing to you, because this is a field at the beginning, is that if you look at all this perturbated series, they show that there is a realistic hope indeed. Let me be a little bit bold, but there is a realistic hope of realizing Paul Dirac dream, namely that of reformulating, I use the word completion of quantum mechanics, into a form avoiding divergences. And indeed, the perturbated series converge extremely fast. It is, you can see this from here, that mathematically you can turn a conventionally divergent perturbated series into a strongly convergent, these isotopic series, because you see the product here, the isotopic element is there, but the isotopic element is infinitesimal. So therefore, the strong convergence is assured. Dirac distribution becomes Dirac delta function, and so on. So there is, it's an intriguing open problem that that we, at least personally, hope to work. And of course, I will be only honored if any of you is interested to discuss it. The next expression is basically the preceding one multiplied by 3 by 3 meters. I would like to do only non-relativistic treatment, because if we add 4 dimensions, then there's too much material to cover and I get lost. So what it is there is what I call geometry. but, you know, Page, you remember when I mentioned the use of geometry, there was some just objection, but I want to clarify that I'm talking here high school geometry, namely we have to represent the proton and neutron as ellipsoid. That's the geometry, because they are rotating proton and neutron. If there is a, so finally, I want to bring to your attention that this isotopic element allows us to achieve a more realistic representation of nuclei as they are now, namely as extended charge distribution in condition of partial mutual penetration. And then once in penetration, the charge distribution experiences a contact interaction, which in my view is the velocity dependent to remember Newton, because Newton will be at the foundation of most, I have to say, in the application. If there is any question, please.
One minor point about a typo, you said you would be interested. I think your expression for the identity is not quite right.
I will not be surprised. Thank you, Doctor. I will correct that.
I just one question. Why is a hat over the eye? That indicates it's a unit. Is that what it indicates?
Well, the hat is because we indicate isotopy. Or we use the conventional symbols, and we put the hat on the top of symbol to indicate that it is an isotope. There is a number n. We put the hat on the top to indicate it is an iso number, and so on. Dr. Pace, could you please?
But an iso number is a real number apparently, because as you're taking the reciprocal of that t hat is larger than 0, so we're only talking about real numbers, I guess.
Well, it's a real number. Well, let's wait for the next transparency, which will be on iso number. Dr. Garrett, if we can wait a few seconds, I will appreciate it.
Okay.
Dr. Pace, where is the misprint here? I will appreciate to know it.
Are you able to see my annotation on your slide?
Yes, I can. Yeah.
Yes. Shouldn't that be an X?
Yes, absolutely. Yeah.
Yes.
Absolutely. Okay. Thank you. Indeed, you see my eyes. That is appreciated. I will correct it in the transparency.
No problem. I do have one minor question too. There's another case. Well, down here in this expression, I was wondering why the first, like maybe I should remove that drawing. This you have psi over psi hat, and I was wondering, that doesn't like if these are isotopic elements. You'd be dividing a non-isotopic element by an isotopic element. So I'm not sure. Perhaps you meant psi hat over psi hat dagger, maybe, or something like that.
Well, it is intended to be in the following sense, but this is best to see the actual transformation of the Schrödinger equation from quantum chemistry into isochemistry, in which you see, but this is, you can to understand this can be also replaced, can be this ratio of two different, at this moment is a ratio between two different wave functions at this level. However, in reality, can be turned into the ratio of two different potentials. There will be the Halton potential on the top and the Coulomb potential at the bottom, because the aim is to switch, the enemy of the valence is the Coulomb, attraction. So the trick of what we achieved is a non-unitary transformation that essentially embeds the Coulomb potential into much stronger attractive force. And that's
but doesn't my question is a little more just technical, because in the exponent, the constant in front of the integral, you have psi over psi hat, but you just mentioned that hat meant that this was an iso number.
That is correct, yes.
So I don't, if psi without the hat is not an iso number, then this is an operation from elements from two different algebras.
Well, the functional dependence of the isotopic element, as far as we know, is totally unrestricted. there operations in once.
No, my question is very specific. Like, I'm wondering why is there no hat on the first psi?
Because the
Right.
first psi is the wave function of the Coulomb related to the Coulomb potential, which is extremely repulsive. And the psi hat instead is the wave function of the Halton potential, which is strongly attractive. Halton potential short distance behave like the Coulomb. So the psi hat, when you look at it explicitly, at short distance is essentially the same as psi, but however it carries however an attraction rather. This Dr. Pace, we should look at to really have some significant discussion. We should look at the actual problem of creating or achieving an attractive force between identical valence electrons. Then we can at this moment I can only say that we never use any restriction on the functional dependence of the isotopic element. And without, otherwise we will be unable to create an attraction between, not only in the case of valence, but also in other cases.
Okay, just let me make one comment. In
Please,
the first line there, why is I hat equal to 1 over T hat is larger than 0? That indicates that 1 over T hat is a real number. It's larger than 0. And the first line.
It's a condition for the isonumbers and isofields that has to be positive definite, but it can be a matrix. Generally, it's a matrix.
Oh, okay, it's not necessary. It's not a real number then. It's
No,
a matrix. Okay.
No, it can be a matrix of operator, a matrix of in this case 3-dimensional. Because
okay, I'm sorry.
No, very legitimate.
That's very important for me though to understand.
This is a very legitimate question indeed.
Perhaps it should be 0 hat. Maybe it would be clearer if you wrote 0 hat.
Well, let's discuss this with the isonumber. That's the additive unit. 0 is the additive unit.
Yeah, so it's the same as 0 in any algebra. But
So we're really thinking about that as just a diagonal matrix with non-zero elements down the diagonal.
Yes, yes, indeed. Yeah. Okay, so with your approval, let's move to the isofield and isonumber where we can discuss some of this question correctly. I think you had the chance to look at the papers I sent you, particularly the book by Professor Ganformina and Nunes, which I would like to indicate the difference. Here I have a somewhat different perspective, exactly in the same presentation. What this series of the presentation that I'm here preparing for your series are intended to achieve a completion of quantum mechanics, and then eventually, according to the EPR, and eventually applied. Now, so the perspective that I am presenting here is that we start here from a conventional numeric field, and then we don't look. Then we introduce the infinite variety of what we call isotopy or isotopes of that field. Because this notion of passing from one to an infinite variety, I believe, is important for a number of geometrical applications. So basically, what I do here, give me a chance to point out. So this is the conventional definition of an ordinary field on which we know the content, the number, etc. And here we consider the infinite variety of isotopies indicated with a hat only where the generalization exists. So the numbers, the elements that are generalized, the product is generalized, the multiplicative unit is generalized, but the sum and the related additive unit are not generalized. This is a difference with the formal definition of isofield, because not only the way I did it originally, but also look at the beautiful definition of Professor Ganforminas and Nunes. They lift everything, including the sum and the zero. However, in practical application, ladies and gentlemen, becomes so just the formalism becomes so cumbersome. And in any case, we have found at this moment no applications for the isotopy of the sum and the related additive unit, which is zero. So So based on the definition is the following. We consider this infinite family of image of the original field. This is an important point to show the connection, because we need the limit of recovering quantum mechanics identically and uniquely. And so where the elements n hat are given by the product of the elements of the original field n multiplied by a quantity at this moment defined as a quantity, assuming here only to be positive definite, but possesses otherwise an arbitrary functional dependence on any needed variable, and is this generally outside of the original field, is generally outside of the original field. Then when those this infinite family of isotopes is equipped, verify the following three conditions. Namely, condition number one, that the multiplication is the isoproduct, which I indicated, reviewed in the preceding lecture, which is now familiar, characterized by new quantity, which we call the isotopic element, also assumed to be positive definite. Then the second condition is that this infinite family as a multiplicative unit to the right and to the f has to be necessarily given by the inverse of the isotopic element. And the third condition is that the sum and related additive units are not lifted, are not completed, are left at conventional. Under those conditions, then all elements of this infinite family of isotope verifies all axioms of a field. And in this case, and in this case only, they are called isofield. And the elements in this case are called isonumbers. Here I have listed all the conditions that I know, depending on the multiplications. Then there are additional conditions on the sum. I didn't write them down because they are conventional. So this is basically the. Here now, Dr. Garrett, here is the question that you ask, what happened to your hyper numbers? Well, I have not studied the case. I think this is intriguing indeed, but I don't think that they verified the axiom of a field in the traditional way. However, what is intriguing is to see whether there exists an isotopic element, T hat, so that indeed the hypernumbers can verify the axiom of a field at the isotopic element. That will be an intriguing possibility. I do not know the outcome at this moment, but I know whether the isotopic element allows you to do tricky things. Indeed, they can be nilpotent. There is an infinite variety of possibility that you have in dimension, functional dependence, etc. Any questions? Shall I go to the next definition or? Very well. So let's move the second. Now the operation on number isofield, we can discuss it, please, at the end of the lecture. The second quantity that is notion that is necessary for to discuss the iso-differential calculus, particularly the iso-differential calculus using that is needed in physics to our best understanding. And this is the notion of isoscalar and isofunction, which I indicated in the preceding very generic lecture. Remember, in physics, the number produced by an experiment have to be elements of the field on which the theory is defined, and the theory that has to be verified is defined. It has to be exactly the same for on the isotopy. Whatever quantity to be accepted has to be an isoscalar. But this implies, however, that coordinates are volume, because the isotopic element represents volume. So this the substantial significant change from traditional line. Functions have to be isofunctions, have to be multiplied by also have to have value on an isofield, so they have to be multiplied. There exists a very large number of papers on the isotopy of special function, Bessel, and you name them. If you are interested, I'll be happy to collect the literature for you. The third and final notion that I need, at least for my limited objective, is the notion of Isoclidean isospace. Again, I want to present it not in as you see it in the literature, but with this perspective, we start from the conventional Euclidean space, which is defined here, and the conventional symbols. This is in 3 dimensions. So R is XYZ coordinate. The metric is traditional delta. The unit is traditionally a 3-dimensional unit. And then we consider the infinite family of images of isotopic completion. I do not know a correct technical name as yet, but it certainly is an infinite family because you have an infinite number of different isotopic element, iso unit per each given original field. In this case, we have Euclidean space defined over the field of real number R. In this case, we have an infinite family of isotopic image defined over the iso field of iso real number, so as to have this continuity under this broad possibility to have a family of different systems. When this family of isotopes first of all, as its multiplicative unit is equal to the multiplicative unit of the base iso field, number one. Number two, when just let me take some equipment. Number two, the matrix is an isomatrix, which means has to be a matrix. Namely, has to be a matrix is a matrix in which all elements are iso numbers. So therefore, the isometric has to have the iso number multiplied for consistency in this formalism of isomathematics. However, the lifting of the original delta is substantial because you start from a delta 111 and you end up with an arbitrary functional dependence. But however multiplied by the iso unit. And condition number 3, the interval in this infinite family is computed in this according to the same rule as we compute the interval in Euclidean space over, but however mainly formulated according to isomathematics, which is essentially via the use of the iso product. Then the statement is that under those 3 conditions, this infinite family of isotope is locally isomorphic to the original Euclidean space. That is the statement which has been discussed and proved in a number of papers. I have to say, however, that a rigorous proof of this statement, in my view, has never been done. And the reason being because it requires generally, this is our correspondence, Dr. Pate, requires the formulation of iso-differential calculus on these isospaces, which has never been done in any. I just do it embryonically, just a tiny little, just to get to see that it exists. But that's the needs indeed. But the implications are rather significant, and that's why I presented here as a conjecture. Namely, that the implication is as a conjecture. Then all this infinitely possible isotopic image of the original Euclidean space, when defined on as a real isospace, then they are locally flat. Namely, their curvature is 0 on isospace. However, when they are projected on the original Euclidean space, then there is the emergence in general of a curvature. Now, again, the rigorous proof does not exist, but the first hint is that this local isomorphism of the iso-Euclidean space with the original Euclidean space, but also look at here, there's a very empirical idea that on one side we mutate, we don't say deform, we want to stay away from deformation. We mutate the metric by multiplying it by the isotopic element. Jointly, however, the unit of the original space is mutated by the inverse amount, and so they cancel with each other. You can also see it here from, in this way, you can start from the Euclidean space. This we can do it, if we look at some application, we start from the Euclidean line element, and then we, which is of course locally flat, and then we do a non-unitary transform. And those conditions, the locally flat character, apparently it carries over. Now, the implication of this trick are significant because in my view, because first of all, this infinite family of isospaces, in my opinion, unify all isospaces, and therefore the related geometry are unified in one single class. Indeed, for instance, the Riemannian space, 3 dimension, is a small, I repeat, the Riemannian space is a small particular case of this family, because the Riemannian space only depends on the local coordinate. This depends on anything, most important on the velocity, as you will see in a moment, to represent contact interactions. And in any case, however, this way of bypassing, this is in four dimension at the Minkowskian level. I use this approach at the Minkowskian level essentially to formulate identically the Einstein field equation. However, in such a formula is without curvature, and then achieved an apparently interesting grand unification of gravitational electroweak interaction, meaning that curvature is the biggest, by far the biggest obstacle for grand unification beginning with Einstein. However, this study indicated also the necessary presence, if you are interested, the necessary study of inclusion in the study for a consistent future consistent grand unification required the inclusion of antimatter. So I published this study at my book with Springer 2001 on iso-dual theory of antimatter with application to grand unification and so on. Unless there are questions, I would like to defer discussions after the iso-differential calculus, please.
There are many questions I have in my mind about this particular comment about geometry and isopity. How should I say that? Isotopy, right? So
isotopy is the same.
Yes, but it's intriguing. Your conjecture is intriguing to me. Yes.
Yeah, let me illustrate it this way. For instance, the very first thing that we did is to attempt, of course, all I'm saying, they're all tentatives, so I beg you, but we try to unify special and general relativity. How? Because they are differentiated by the isotopic element. In other words, the Minkowski metric exists in both the Minkowskian as well as the Riemannian. But in the Riemannian, you have to factorize when you factorize the Minkowski geometry from the Minkowski metric from Riemannian metric, you end up precisely with positive definite isotopic element. So you see that there is a realistic possibility of achieving a grand unification of the, because the ultimate the physics beyond this is that the ultimate axiom have to be the same for both special and general relativity. Doing in this way, you emphasize that point.
Of course, Einstein also worked in this area and in particular studied teleparallel geometries as a possible way of presenting gravitation.
Yes.
And these teleparallel geometries seem to be related to what you call null isocurvature, I think.
That's very interesting, very interesting. But that's in 4 dimensions, let's stay, or 3 dimensions in this lecture, because those things are so intriguing. And when you add them, when you add living organisms, oh, they are so stimulating that it becomes really exciting. So,
and of course, differential geometry is a very big subject, and in particular, I would mention Riemann-Cartan's approach to geometry, which one has to clearly define what one means by curvature, because there's both like Cartan curvature and Riemann curvature, and they are 2 different things.
This is a third different notion of curvature. Yes, indeed. Yeah.
But related somehow, perhaps.
I think
Jesus,
so.
Jesus, you had a question?
No, I have too many questions. Too many questions. And I was trying to understand the ISO numbers, like one kind of transformation of in the product, only one part of the product. Then I apply T to one part of the product, and the other is the normal numbers. Then this is like a kind of scalar product or interior.
I think there's an implicit isomorphism between, like normally an isotopy would be written in terms of a function on each of the parts of the product, right? So we like F of the first part and G of the second part, right?
You are absolutely correct.
But then you just take F to be an identity, right? So then.
Yes.
There is a lemma in the literature that isofields are locally isomorphic. The whole infinitely isotopic image of an isofield are locally isomorphic to the original field. And you can also see it in a different way. The isofields are constructed by a non-unitary transformation. So you have a number, you assume a non-unitary transformation equal to the iso unit, and then numbers are transformed into isonumber. The conventional product is transformed into the iso product, and you get everything. So everything uniquely and unambiguously. So, and this also will illustrate the local isomorphism of, in other words, isonumber are another abstract way of expressing conventional number, of expressing the aim, the physical aim is, as well as geometrical, is to identify concretely the degrees of freedom in the axiom of a numeric field. The realization, they are equivalent. I see physically a difference between real number and real iso number. Physically, there is a big difference because iso unit can be an integral differential operator. Well, mathematically, I don't see any mathematically, they are the same.
But these are associative, right?
Yes.
These are associative operations. So
yes,
you don't really want to think of T as operating on the second part, right?
No, T is defined here by in this the product, which is the conventional associative product. But careful because it's generally associative. But you see here the condition is not necessarily isocommutative. Like the same ordinary number, quaternion are not commutative. So everything that occurs for number occurs here uniquely and identically. So definitely associative. And there are problems when but the simplicity in this case is because we don't include the sum, the isotopy of the sum and related unit. Because in this case, 2 plus 3 may become minus 250 because you change the basic unit.
Yeah, I just like to make one comment.
Please.
Originally, I guess quantum mechanics was formulated by Heisenberg without using matrices. Then later on, it was proven to be equivalent to Schrodinger's matrix approach. And I'm just wondering, could you formulate your isocalculus totally using matrices?
Oh yes, indeed. Indeed, that's our isotopy of the. You will see in this lecture, hopefully, the isotopy of the Heisenberg representation is expressed in terms of matrices.
Okay, so everything could be formulated in terms of matrices then.
Absolutely, the iso unit is a matrix. The isotopic element is a matrix.
Okay, well, this is very interesting because geometric algebra also can be formulated totally in terms of matrices. Thus, it's clear that we could merge our two languages together.
Absolutely, indeed. Actually, it is our primary representation in terms of matrices. You will see this in a moment. Very well. So let's stop as far as the isocalculus geometry because the question are many all pertinent and all the intrigue. This idea of a point and isospace is a point. However, the projection in our space, it is a curve. This is a definition of isovectorized space. I don't want to read it because it takes the entire lecture, but this is from Professor Ganformina and Nunes. I mentioned because I believe that their study of isovector isospace are important for Professor Odziewicz's study, because in my opinion, they broaden the concept, the realization, not the conception, the realization of Professor Odziewicz. By broadening the realization, you increase the possibility of applications. Well, unless there are questions, let's go to the iso-differential calculus, if I may. Any other question, discussion, let's do it at the end, please. If you agree, of course, I don't want to impose on you. Very well, so let's look at the situation in the early 1990s. The situation of hadronic, the completion of the EPR completion of quantum mechanics into hadronic mechanics. Well, the first situation was Einstein, powerful criticism of quantum mechanics, that is a strictly local theory that can only be defined at a finite number of isolated points. That's the case for the wave function, that's the case for the potential, that's the case for the differential. But let's look at the isotopy of the Schrödinger equation at that time. We had enlarged the coordinate in the isocoordinate, that's volume, yes. Isotopic element can indeed be defined in volume, yes, indeed. Potential is now defined on volume, but you look at the differential part, is a local differential. We used to call this a minestrone, the Italian way, a minestrone, because there's no, in my opinion, there's no future. That was we never published anything, because the theory is clearly inconsistent. The origin of the problem was here, the linear momentum. We did not know how to formulate the linear momentum of hadronic mechanics, because it is defined in terms of the partial derivative. And the moment we use the partial derivative, everything blew. I lost invariance of the numerical prediction over time. But at the same time, I couldn't calculate the angular momentum. I couldn't calculate so out of desperation, I had to reinspect the axiom of Newton-Leibniz differential calculus. And I wrote this paper at the Joint Institute for Nuclear Research in Dubna. It was 1994. This was in preparation of a major international conference that we held in these topics in 1995 at the Castle Prince Pignatelli in Italy. It was 150 participants, huge conference. And I submitted the paper to the Rendiconti Circolo Matematico Palermo, the best Italian journal, Pure Mathematics. The editor, my paper was 80 pages long, but the editor was so excited that he added other papers and released a special issue of the journal, volume 42, 1996, under the title Isotopy of Contemporary Mathematical Structure. This is, ladies and gentlemen, this is the most important paper that I've written. Everything I have to say here on is in this paper. So first of all, let's get started with the definition of the iso-differential, which is the most important of everything I have to say, as well as the most important concept of in which I need all your criticism. Here I need solicit all comments, above all criticism. Here is the main idea. I repeated the idea published in Rendiconti, accepted by Professor Georgiev, the leader in iso-differential calculus, but you never know. So the idea is the following, that the infinite family of the differentials of an isocoordinates defined on over an isofield are called iso-differential if and only if they coincide with the conventional differentials whenever the isotopic element is, or more precisely the iso unit, is independent from the local variable, or it is a function not dependent from, depending on whether the iso unit is a constant or a function not dependent by the variable of the differentiation. So here is the identity that defines. What is the aim? The aim that I was aiming at that time, and I continue to aim now, is to give an expression that allows the most general possible number of different, not necessarily identical formulation, but they can be, however, axiomatically unified under the axiom of Newton-Leibniz. And then you can see this the variety by noting that I in the same paper I introduce a realization, but this is a restriction on the infinite families, which you will see better by. We'll comment soon on the Professor George's papers. I propose this realization, namely that the iso-differential, under the condition that we have indicated, the iso-differential can be reduced to the ordinary differential, namely no hat, with the factorization of whenever there is a factorization of the isotopic element. This is clearly restrictive on the definition, but is a physical condition, as we will see soon, not necessarily mathematical, which means there is still a lot to be done in the differential calculus, in my view. And indeed here, please check the little equations. And indeed, you use this definition, and then indeed you can see that the iso-differential reduces indeed to the ordinary differential. Please check out that indeed is the case. This is for the case of what we usually do. We remember we do contact interaction caused by mutual penetration. Those are velocity dependent. So we use isotopic elements that are dependent on the velocity, and so therefore they do verify this condition. And as it is, however, here is the important point. However, if you look at the explicit expression, you see the recovering of the ordinary differential, but you see an extra term. Ladies and gentlemen, this is the extra term that I believe illustrates the main point of our studies, namely that quantum mechanics, even though, of course, a good provide a good first approximation of nuclear fusion. This is out of question. Nuclear power plant, they still work, and they do work well. But so it's an approximation out of question. However, quantum mechanics cannot represent nuclear fusion in an exact form. And here you see the birth at the level of the differential calculus. This implies changes in the engineering in which we build the reactor. And here is the case of the iso-differential for the simplest possible case suggested by Dr. Garrett. But as you can see, it becomes non-trivial. I will appreciate comment on the main point, namely if I succeeded with a very simple and basic condition, I succeeded in giving, opening the door to a large variety of not necessarily equivalent conception of differential calculus. Please express your comments.
Again, I'd like to see geometric interpretation of elements, like what is a vector or a bivector? Is it possible to express those ideas in terms of your language?
Yes, I believe so indeed, Dr. Garrett. But that's the intriguing part of this field, that there is so much to be done. It has never been done. And if you write a paper on it, it will be the first.
Well, I'd like to write a paper with you on expressing.
I will be only honored. I will be only honored. Absolutely, I will be only honored indeed.
There are two theories that really are basically related to matrices. Geometry gives a total geometric interpretation to matrices. Therefore, we should be able to give a total geometric interpretation to your ISO theory. Now, I imagine you have formulated this totally in terms of matrices before, but your language is totally new language interpreting matrices then.
Well, the matrices come up specifically when we work with the so-called iso-Heisenberg representation, which is it's because they're talking about now the Lie-isotopic algebra. The structure is a Lie-isotopic algebra, and then we go to the Lie-admissible algebra, all necessary in terms of Lie-admissible for irreversible system. But the foundation are here. The foundation are here on the foundation on this term here, and those are the implications. We have built machine. We have worked for years at nuclear fusion, and we know I know these things, and I know this from an engineering viewpoint. maybe one day, if you are interested, we can review those efforts, and so you can see this iso-differential calculus. But you have to see its necessity in the next
I would have a question about the differential of the ISO unit. Like that's the last part of your expression there. This.
Yeah, the axiom, the definition is that the d hat, r hat, has to be equal to d conventional, r conventional. So that's the condition. That is collapsed into a conventional because it has to express the degree of freedom of Newton-Leibniz calculus, which is another, of course. So we're talking about the degree of freedom of the right-hand side, which is expressed on the left-hand side.
Interesting. And that last expression there, that last equation is.
It's for you.
Very interesting.
That's for you, because you asked for the simplest possible. And let's pass to the partial derivative. The partial derivative is which we use mostly in applications. But the partial derivative is the same spirit, namely that the infinite family of possible partial derivative of an isofunction or over an isofield are called isoderivative if and only if the differential of the isofunction on an isofield coincide with the conventional differential of the function on a conventional field whenever the iso unit is independent, is a constant or is independent from the variable of differentiation. So this is the axiom. This is the restriction that I introduced among many different possible realization. And this is the condition which we use for the partial derivative. That's what you have to see the application of this. So that namely the isopartial derivative can be equal, can be reduced to the partial derivative by the mere factorization of the iso unit. Remember, for the differential, there is the factorization of the isotopic element. And so for the partial derivative, the differential here is on the iso-differential is here on the denominator. So this necessarily has to be the iso unit. Please check this little equation if there is any error, because then I have to review. In other words, is a proof that indeed this restriction, this realization, verified this basic axiom with very elementary.
Yeah, this almost looks like you're taking a trace. If you thought about in terms of matrices, that first equation there in your definition would be like a trace, perhaps, or something.
Beautiful, bravo, indeed. Very closely connected, indeed. Everything can be reformulated.
Oh, that's extremely interesting in relationship to geometric algebra.
Oh yes, because here you're talking about the unification of all geometry in 3 dimensions. And all been expressed with one single formulation, the broadest possible formulation of the iso-differential, not the simplest possible, the most general possible formulation of the differential calculus. And so you really have, and then you can see the difference between Euclidean and Riemannian and Finslerian, non-Desarguesian, and all these are different geometry. They can be reduced to a single, but we call it isotopic unification, in the sense that they are unified. They are isotopic in the sense that they become differentiated by the iso unit. And normally they are differentiated by the metric. And no, we differentiate them. Very well, let's see them.
I had one question there in the previous page.
This one?
Just one. No, what was that? Okay, next page. Oh, yes, well, this one. In particular, you say constant I hat.
Either constant or a function independent from the local variable, but the variable of differentiation, namely dependent on the velocity.
So this is not for all possible I hats, but only for
It's only for a subclass. It's restrictive over this definition. There are other, I will show it to you from the work from Professor Georgia. Yeah, which I will
But
comment.
from the previous slide, though, you did refer to D I hat. Right?
Yeah, but because it is now the differential is in the denominator here. So here you can have a delta F divided by delta R hat. So here the isotopic element will appear here in the denominator. So for consistency, the factorization has to be on with the iso unit, which is the inverse.
I'm still having a bit of trouble understanding the differential, like the differential of a constant I hat.
No, the I hat is factored out because it's constant. But careful, because it can be, in our case, it's a function depending on the velocity. So it's non-trivial.
So there still exists the concept of the differential of this constant.
Yes, indeed. You can see it here. This is the actual definition of the differential for an actual for the iso unit, actually dependent on number of all the values you want. This is the actual expression. It's non-trivial. Again, you recover the conventional. This is for under the definition of isoderivative. Careful. And only in that case, then you recover the conventional differential, but then back again, you see an extra term. And that's all the novelty. This is, I have no words to indicate the actual novelty. You will see them in a moment, the next transparencies. But so basically, this is an axiom to restrict all infinitely possible generalization of the notion of Newton-Leibniz notion of differential, and to illustrate its freedom. And this second definition is basically to impose what is the condition sufficient for significant physical application on the notion of a differential of a function. So the notion of differential becomes, the fundamental quantity in the isocalculus from an axiomatic viewpoint. It is possible to introduce additional axiom indeed, but from an axiomatic viewpoint, I believe that the differential is the fundamental one. Now, if you look at if you have the time, with no obligation, I beg you, Elements of Hadronic Mechanics, Volume 1, you'll see the actual derivation of the iso-differential obtained via the isotopy of the conventional definition of the differential, the same for the partial derivative. But this is essentially the summary. Again, I want to emphasize, you're a mathematician, and I want to emphasize that this is a restriction on the infinite class of possible broader calculi that are apparently hidden in the axiom of Newton-Leibniz, a notion of differential calculus. Now the so please verify that those conditions indeed are verified, that the conditions are correct. I checked them out a number of times, but with my eyes. So this is, for instance, the definition of the second isoderivative. Again, is a restriction. There are a number of additional degrees of freedom here, but there's a restriction that is needed to do calculation in physics. And this, so this restriction indeed seems to verify the condition of second for the second isopartial isoderivative. This is as a consequence, we have this iso-Laplacian. Remember the minestrone that was hadronic mechanics in the early 90s? Well, this is the resolution of the minestrone, because now iso-Laplacian of an isofunction, you can see you apply all the preceding rules, and you see the embedding of the isotopic element in with the very, very partial derivative. what is the geometric meaning? Geometric meaning is one of the most important, several important physical feature of what we are studying. We are studying interior problems, then for extended particle. One of the most important geometric feature is anisotropy and inhomogeneity. Now, I cannot treat inhomogeneity because it can only be treated with the fourth component, that's space-time. However, the anisotropy, which is evident in a proton and in a neutron because they are spinning. They are anisotropic object, and it is crucial. That is why not only is it crucial to represent the dimension of the proton and the neutron. That's only basically insufficient. Number two, we have to represent the shape. The shape is represented by those semi-axes, still not enough. This has to be invariant over time. Otherwise, the theory cannot be experimentally verified in a consistent way. In my opinion, this is the case for deformation. This is the rule, the simple rule on isotopy for the isoderivative of the isoproduct of two isofunctions is very, very elementary. And this is the proof. Again, I feel a little bit ashamed to call it a proof because it's so elementary. But this proves this definition here. If you have any objection, I'll pass to the next. Please, now is the moment for criticism.
Hey, let me take a picture of that slide. It's very interesting.
I'll send you a copy of the PDF. I'll send you a copy of the entire
Yeah, please send me a copy of all the slides for this talk. It's very interesting.
I'll send you the entire PDF PowerPoint. I'll send you the PowerPoint, please. And after correction, because Dr. Page has located a mistake, so I'll correct it, of course. And I'll give another check, but with my eyes, I will do my best. But
it's extremely interesting.
Dr. Pace, do you want a copy of the PowerPoint or not? Shall I not?
Oh, yes, please.
For me too, please.
Very well, I'll be delighted. Anybody else, please? Okay, very well. Okay, so let's do the next definition, also included in the Rendiconti paper. Give me 1 second, I have to lower the temperature of my room, is getting too hot. I apologize, but thank you for your patience and tolerance. So this is definition of iso-integral, also included in the Rendiconti paper, in which here is the definition. Again, is a restrictive, but it's the one that I use for is compatible with the preceding definition of definition for the iso-differential and iso-derivative, but it's not necessarily the most general one. No. But this idea, the iso, see the hat here, here you see no hat. So the iso-integral can be reduced to ordinary integral, provided that the integrand is multiplied by the iso function. And indeed, with this definition, you can see that iso-integral of an iso-differential, of an iso-variable is equal to the variable. So this indeed does the trick that I need in physics. The same, the iso-integral of the iso-differential of an iso function gives you the iso function. This is exactly what I need in physics. So this is a very limited definition, and essentially are what I need in physics. I didn't because then mathematicians have taken over, particularly Professor George of the Sorbonne, Department of Mathematics, Sorbonne University in Paris. He has written a monumental work in which I send you personally for personal use the monograph, which I believe they're crucial for application in physics, particularly to energy releasing processes. But I want to elaborate on first of all, you see that the condition for a function to be an element of the iso field is a physical condition. I needed to get invariance of the numerical prediction, but the mathematician doesn't need that. So here you see this is an initial classification of iso functions in Professor George's first volume. Then you go later, you see others. but in which the definition of isofunction occurs only in the second. But for him is one, you see, so the moment you weaken the condition that the function has to be an isofunction, then you immediately broaden dramatically the variety of the iso-differential that you indeed are allowed. Here you list three more. For us, the last two are not necessarily, for us three are independent, because the fourth one is connected to the third by what we call isotopic inversion.
Could you say one more word about that example with the x hat on the right? Could you say a little more about that equation? What is x hat exactly?
Could you tell me, is in this transparency or before?
Yes, in your examples, your first simple examples of that integral relating dx hat to
this
x hat.
This one?
Yeah. But can you say more about that example?
Yes. Here you have the iso integral. You see the hat of the iso differential. You see the hat of the iso function. You see the hat. And now, according to this rule, again is a restriction, is a rule, and then you see the iso integral is reduced to the ordinary integral. There is no hat, but the iso differential has to be multiplied by the iso unit. But there is the rule that the iso differential is the isotopic element multiplied by iso coordinates, and so therefore the isotopic element and the iso unit, they cancel each other, and you reduce to this expression here the integral of the differential of x, so therefore this is equal to x. I apologize, I should have written down, the step is missing here, and thank you for asking the question, Dr. Garrett, I appreciate it, because I should have written down an intermediary step in which you clearly see that the substitution of d act with isotopic element multiplied the ordinary differential. So iso unit and isotopic element, one inverse to each other, they cancel each other, and you reduce to this expression. There's a one inverse to the other, you get, and the same here, same rule, yes.
I'm just again wondering exactly about x hat, or the next equation, the same thing, how you interpret x hat. I usually interpret x hat as a unit vector, but obviously that doesn't work here.
No, provided it's an iso, in my opinion, this is, I believe Professor Gunn, I'm not sure, but Professor Gunn-Formina and Nunes will tell you, yes, but it has to be an iso vector. So you should look at the definition of their definition of iso vector space. Very, very intriguing, because you cannot do this in you cannot re-express this theory in terms of conventional applied mathematics. No, I would not recommend it. You will end up sooner or later with the controversies, inconsistency. But if you do it isotopic, so in terms of iso vector, yes, absolutely. Because,
well, how about a x hat? Can you interpret that as a matrix? What matrix would that interpret?
yes, because the x hat is a volume, is an ordinary x, an ordinary number multiplied by the iso unit, which is a volume. Wait a moment. Let me see.
Okay.
See. This is
that's good.
This is what you have to figure out in your mind. This is an iso number, or in this case, it's an iso coordinate. But careful, because if you are at the abstract level, iso space is over iso field, then it is a point. Yes, because isostopos. Whatever you have in the Euclidean geometry, you get in the iso-Euclidean isogeometry, identically at the abstract level, to such an extent that this is a good rule to check equation. That the equations and of everything of the iso-Euclidean isogeometry can be written with exactly the same symbol of the Euclidean geometry, identical, no change. Only the interpretation of the symbol is different. The products are isotopic, the differentiation is isotopic, but the symbols are identical. So when you are at the abstract level, a point in Euclidean space remains a point in iso-Euclidean isospace. However, when you do the whole novelty is in the projection, and then you see that it becomes a line. A line, for instance, a line, this is a conventional line, when you go to the isoline in this space, becomes a tubular form with ellipsoidal section. And then there are all sorts of intriguing, but it's better we don't start with those things because we got lost on. So I have no word to express that this is a field in which basically my primary interest is a very powerful unification, but not conventional unification, this new type on which even the name is debatable. I call isotopic unification, but there is so much to be done. And so, but let's unless you have question on the iso-differential calculus, I would like to pass to to illustrate its mandatory character. Okay, so let me go to the. This is the foundation of analytic mechanics. This is the Newton's equations written according to my first volume at Springer log. SS means the condition of variational self-adjointness, integrability condition to admit a potential. NSF means variational non-self-adjointness. So the Newton's equation, the majestic conception by Newton can be divided, this infinite number of forces he conceived, can be divided, those derivable from a potential in those that are not derivable from a potential, which are the velocity dependent, the resistive force, the force of nature, the reality. It is my opinion that during the past 4 centuries, and I want to stress this point because I hope to stimulate your contribution on this point that I consider truly fundamental. And there is so much to be done. In any case, there's no dream for me to do it alone. But during the past 4th century, we have only studied this part of the Newton's equation. And the biggest part has been essentially ignored. Now, Lagrange didn't do so. Giovanni Luigi Lagrange, he lived in Torino where I had my PhD. I studied his papers in Italian. Lagrange got it. He got it indeed. He got it fully. And because he said that the potential, the forces derived from potential will represent with a quantity, he called it in a strange way, now we call it the Lagrange. And all the other Newtonian forces are outside, they're contained in the outside. Lagrange ended to say that this is expected to be the analytic origin of thermodynamics, namely because all those forces are contact interaction. And he said they were expected, he didn't work it out, but essentially, but he hinted that you study at the statistical level first, and then the thermodynamic level, these forces may indeed be the origin of the entropy, essentially. Hamilton followed Lagrange identically, and Jacobi also, the fall of them. Lagrange put Hamiltonian for potential forces, the external forces. Now, I spent this is my PhD at the University of Torino. I initially started with those bases, which I consider fundamental. Those are the true Lagrange and Hamilton's equation. The one used in the past century are truncated. The good part has been removed. I could not use this part. This is the first meaning that I want to, in this remaining part of this lecture, my dream is to indicate you points which can avoid you to spend years of your time, of your research, and then discover that the avenue is not the correct one, as it happened to me. I have a few of those cases I want to report to you. This is the first. You see, I first spent a year and a half, because this is my aim. I want to represent the entire. Why I have to represent only a little part? No, let's try to represent all. Then if I fail, it's okay. I couldn't use it, this analytic formalism. Why? Because when you compute the time evolution of an observable, here is classically, the time evolution of a quantity, A, according to Hamilton's equation, what you get this expression which characterizes a triple system. Is no longer bilateral, bivalued, is not a bracket that verifies right and left axiom for to characterize an algebra. So, to my knowledge, this doesn't characterize. So I will lose not only I will lose all the algebra, but I will lose the notion of algebra. I just couldn't do it, and because of this, you should look at my second volume that I published with Springer-Verlag, it contains two main parts. The first part contains the Birkhoffian mechanics, and the second part, the foundation of hadronic mechanics. The word hadronic mechanics appear in that volume for the first time in a serious publication, except memoir. And but this included the second part included the Lie-isotopic completion of Heisenberg equation and the Lie-admissible isotopic. The two parts, however, while the second part has remained fundamental, still as of today, it's not changed. However, the two parts have remained completely disjoint. And it took 20 years for me to resolve this disconnection. I want to tell you my experience because can help you. So, so the first thing that I did, I did achieve universal. Sorry, we call direct universality in the representation of all Newton's equation. Universality in the sense of representing them all is not enough. Then they have to represent it in the coordinates of the experimental without the coordinate transformation, otherwise it becomes trivial. And then, so that's the notion of direct universality in those volumes. So I did achieve direct universality with the Birkhoffian mechanics. And the Birkhoff, not only with the Birkhoff's equation, they essentially, they are the equation of truncated Lagrangian Hamilton's equation, but written in 6 coordinates, which is six-dimensional, the 6-dimensional phase space in R and P. So, I not only represent them all, but I represent them with a variational principle. So I thought that I will have a capability to a naive quantization and pass to the operator level. No, I failed. I failed to achieve. I want to illustrate why and what happened later. Well, let me apply the iso-differential calculus, and then you see the mandatory character. After the 50 years of this thing, if you have any alternative, please, I'm interested in science. I went to Harvard because I was interested in science. I had no interest in a career at Harvard. I think it shows from my record. And that's been the rest of my life. So this is the representation of Newton's equation via the iso-differential calculus. Let's look at the equation themselves. These are the equations, as you can see. They are reproduced here. Now, what you see is only the appearance of the forces derivable from the potential. So the question, where are the other forces? They are embedded in the differential. In this case, the differential of the velocity. So the iso unit is velocity dependent, because the velocity dependent is one of the most important concept of contact interaction introduced by Newton. Now you write explicitly this differential by using the little rule that I indicated before, and you get this expression. So you get except from the factories by removing the common multiplication by the iso unit, you get indeed the entirety of the Newton's equation, and also you can represent them all, because this equation here always admits a solution for regular interactions. You can see more accurate proof in the Rendiconti paper. Again, everything I have to say is in the Rendiconti. So now immediately you go to Lagrange equation, and the isotopy with iso-differential calculus, and only with iso-differential calculus, particularly with the iso-partial iso-derivative with respect to the velocity or the momentum, if you want, here. Then immediately you see the disappearance of the external terms on the right-hand side, but they're a full representation with iso-partial iso-derivative. And exactly it's the same for the Hamilton's equation, in which those non-potential forces are represented with the degree of freedom of Newton-Leibniz differential calculus. What is the implication? The implication for me cost me years and years to reach. Look at here, the time evolution of an observable based on Hamilton's equation. The time evolution is very elementary, given by this expression. But this indeed verifies all the axioms to characterize an algebra. Not only that, but this algebra turned out to be the axiom is to be the axiom of the Lie algebra. So this is isotopic because of the broader realization of the partial derivative. But all axioms of Lie are verified. So this gave me hope that eventually we can complete quantum mechanics by conserving its basic action, because the emphasis, before we change those actions, let's see what the broadest, everything we can maximally do before abandoning those actions. I am not ready. The deformation theory abandons the action. I never did. But anyway, so I want to indicate that this importance of but here is the point. In this equation, this essentially cost me 20 years, this equation here. What is the problem? The problem is the following, that if you look at the second volume of Springer and Lark, you see the Birkhoffian mechanics, and you see also the Birkhoffian version of the Hamilton-Jacobi equation. Incidentally, first you see the representation of the Birkhoffian mechanics. You see representation of everything with a variational, with an action principle. So Birkhoffian mechanic was fully successful in allowing an optimal control theory, optimized shape, for the first time that I know, in the presence of Newtonian velocity-dependent resistive forces. And indeed, it has been used by engineers more than physicists in a number of, I continue to be consulted by engineers precisely because the only optimal control theory they can use in real cases. And now, if you look at the Hamilton-Jacobi equation for the Birkhoffian mechanics, this last expression is that this partial derivative of the Birkhoffian action with respect to the momentum is not zero, is equal to something. What does this mean? Well, this means that the wave function, as we will see in a moment, that the wave function of the operator mechanics that you can easily construct from those expressions via naive quantization or symplectic quantization or whatever, the quantum mechanics, it depends necessarily on as isostates and the wave function, that depends necessarily on both coordinates and momentum. I repeat, the stumble, that 20-year stumble with Birkhoffian mechanics, after achieving universality, variation of everything was there. And I had to stop because unsurmountable mathematical difficulties, but also questionable issue pertaining to basic action. The unsurmountable basic difficulty for me were the following. I was unable to operate, to manipulate a generalization, a completion of quantum mechanics in which the wave function will depend on both coordinates and momentum. The complications were so complicated, even the simple equation became so big that I felt discouraged. But that's not enough. If you accept Birkhoffian mechanics and you make and you construct an operator image, which is possible indeed, indeed it is possible. However, you can see that you have to necessarily broaden the axioms of quantum mechanics, and which is something I didn't feel like that it should have done. At least I should try something simpler before that. Now, and so that's why this I decided to go back to ground zero. After 20 years, this Birkhoffian mechanics, 1978. I said the differential calculus, 1996. So I'm talking about 20 years. So look at here now. When this is the representation of the iso-Newton's equation with the iso-variational principle, and is universal, directly universal. You represent them all those equations. Very easy to prove it. And then very easy to prove this isotopic form of the Hamilton-Jacobi equation, which the partial derivatives are isotopic. But here is the important point that finally resolved this 20 years long riddle, that the isopartial derivative of the iso action with respect to the momentum is zero. So this, in my opinion, is extremely important for the only possible with iso-differential calculus. No other way that I know. It's crucial for the maintaining the axiom of quantum mechanics under DPR completion, and as well as to simplify to avoid the extreme complication of a complication of quantizing, so to say, Birkhoff equations. So, but nevertheless, you are a mathematician. If you are interested in a very interesting project, careful that you will abandon quantum mechanics. You exit. You don't abandon. It's a particular case in any case, but you exit from quantum mechanics. You exit from the class of non-unitary equivalents of quantum mechanics, which is hadronic mechanics. Okay, so if you're interested, then please do it. And let me know. I would be interested looking at your and honored for any collaboration you think that deemed applicable. Here, let me close this transparency with a very fundamental notion, also a delicate notion that I have to indicate. Give me 1 second to clear my nose. Sorry. I apologize. I'm sorry. Okay, this is the naive quantization. If you go to the level of symplectic quantization, we have constructed the rudiments of the isosymplectic geometry, so everything carries on the isotope. So this is the naive quantization, the action of the truncated Lagrange equation gives rise to the log of the wave function. And now this everything carries trivially at the isotopic level, so the iso action maps into isolog, which is the iso unit multiplied by the logarithm of the wave function. What is the delicate point at which I have to tell you honestly here, because we are scientists, we have to look at reality as they are to the best of our knowledge. The point is that according to the iso-differential calculus, and consequently according to this type of completion of quantum mechanics, Planck's constant is no longer a constant. This means, and because it's replaced, but see, there is a Planck constant here, is replaced by the iso unit, which is an integral differential operator. This means that energy exchanges according to hadronic mechanics are no longer necessarily discrete. I repeat, energy is an inevitable consequence of the theory, whether you accept it or not. This is the consequence I want to very honestly indicate. And intuitively, let me tell you very bluntly my personal feeling. While I accept for beyond any doubt that energy exchanges of an electron when it is orbiting in vacuum around the proton are discrete. This is beyond this 1 century of evidence. This is absolutely not the point. This is beyond any. The issue is the following: that even to accept that evidence, it is impossible for me to accept that the same electron, when it is in the core of a star, when the same electron is in the core of a star, you think about here, think about all this square root as is the entire of the star. When the same electron is in the core of a star, for me it's impossible to accept that electron has energy exchanges which are discrete. Why it's impossible? Because you cannot do energy absorption unless you have jumps, unless the orbit is changed. How can the electron jump to another orbit when this electron is under an astronomically incredible pressure from this the ultra dense medium? And but there is something delicate also I would like to indicate, which is connected to this issue. So this idea that the energy exchange of this electron depends on process connected with all the environment. That's the idea of the non-locality of the EPR entanglement. This is not my idea. This is the idea of Prince Louis de Broglie and the physicist David Bohm. That theory is called the non-local completion of quantum mechanics, the de Broglie-Bohm theory. It is semi-classical, it's beautiful, and it's naturally very naturally connected to the recovery of Einstein determinism sorry. I'm going. I apologize. Okay. So it's connected to the the de Broglie bomb, non-local theory is connected to recovering of the Einstein, the progressive recovering of Einstein determinism for this electron and it is connected to the isotopic element. The product of the uncertainty for coordinate and momentum becomes, in this theory, becomes proportional to the isotopic element. The isotopic element is infinitesimal. In those conditions, when the core star is practically zero. So therefore, here you recover Einstein determinism. But back to the de Broglie role, you should know that they were under extremely severe. Particularly the de Broglie was a Nobel laureate at that time, so he was very authoritative, and he became under severe pressure by colleagues. His wife, the Princess de Broglie, became under pressure from the wife of the colleague, so that she had to convince the husband, the prince, not to publish nothing on his non-local theory. Prince de Broglie eventually, Professor de Broglie eventually accepted, and he never published anything. The idea were resuscitated by David Bohm, and it are justly known as the Broglie Bohm theory. Why all those pressures? Because it was known at that time, and of course it is well known today, that all those non-local effects implies they appear to violate Einstein's special relativity. So you should be aware that this is an inevitable consequence. Whenever we speak about the completion of quantum mechanics, we speak also of the completion of relativistic quantum mechanics. And therefore, but the relativistic quantum mechanics is based on the special relativity. So therefore, a suitable revision of special relativity is unavoidable. So this is basically the origin of a century-old opposition against the study of the Einstein-Podolsky-Rosen argument. However, I should say that, but this the past is past. It was the routine. I smile and laugh at it. This is a routine process, you know, in science. The disagreements. It is absolutely routine. Here I would like to take the opportunity of give me a chance of 1 minute, because I have to express my appreciation for some of the biggest support I have received in those studies to date, which is precisely from colleagues from Israel. Allow me to indicate it briefly. First of all, we had this 2020 international teleconference because of the help from the Family of Israel Foundation. I made very clear to my friends in Israel that I will not do the conference unless there was a participation in the organization committee of somebody from Israel, because this was dedicated to Einstein-Podolsky-Rosen. Well, that made no sense. Now, the president, Professor Pinchas Mandel, is a former member of the Mossad. He has in record very dangerous missions, not only for the security of Israel, but also for the security of our security. Our apparatus are very, very closely connected. Thanks God. The same for Italy, very, very closely connected. The members of the Family of Israel are mainly medical doctors that are interested in the biological application, but they are also there, which includes everything. The second, but I would like to indicate also the support from many physicists, such as Professor Horvitz, Tel Aviv University, my personal friend. Yes, I have been honored by his friendship, one of the biggest theoretical physicists, I believe, of the 20th century. They invited always me to present isotopy, these things at the meeting of the relativistic dynamics that he organized all over the world. I was invited to plenary speaker. But I have many other episodes. I want to close, not to make it too long, I want to close with very nice episode, because the episode of decency in science are very rare, and so they should be quoted and acknowledged. Back in 1999, this was remember in America, in Boston and Cambridge, there was the total financial disaster. 89 was the collapse of the bank, but the biggest, all banks collapsed. So I had no money. And But there was the Marcel Grossman meeting in gravitation organized at Jerusalem. And so I said, well, let me send the paper and see whether whether I can do anything. And the paper was was this idea that this new geometry by locally isoflat to attempt a grand unification between gravitation and electroweak interaction using the Einstein field equation, no change in Einstein field equation. Okay, so the organizer, Professor Piran, first of all, accepted my paper for publication in the proceedings, even though I did not pay the participation fee, and it was very nice on his part. But he went overboard, and he asked the head of the session in which I was supposed to present the paper. There was Professor Hell from Munich, to present my transparency. And he apologized that he had exhausted all funds with so many invited people from all over the world. He had no more funds to pay my trip to Israel. So I want to quote this. Is a documented fact. You can see the paper in the proceedings. Marcel Grossman meeting on gravitation, 1999, held in 1999. Professor Piran, one of the editors. Ruffini from Rome was another editor. So in conclusion, I want to say that there is this very strong opposition, which is part of a natural part of science. Science is part of this. But however, and now particularly the environmental problem, they are restricting the opposition now to a very minute part of the Orthodox community, if I may say, in my view. Let me close this with this last transparency, and then we can discuss. This is essentially the operator, the hadronic mechanics, the isomechanics. And this is, if you are interested, I have a nice paper from Professor Jung, the mathematician, and myself in 1981 on the iso-Hilbert space. It's called Hilbert-Jung-Santilli isospaces, in which you can see all the property of the isostate depending only on the coordinate. In this case, iso-coordinate, but not iso-momentum. And notice the isonormalization is for the isotopic element, because isotopic element can be a constant, so it can get out, and you have to, otherwise it will be inconsistent for an iso unit. And notice the iso expectation value have two the isotopic element. That's why we represent exactly the fit of experimental data, Bose-Einstein correlation. But this is the equation that costed me 20 years of search, and it was solved finally by the iso-differential calculus, namely the formulation of isolinear momentum according to, in a way, compatible with isomathematics, which thanks to iso-differential calculus projected in an ordinary Hilbert space. Then you see the appearance of the isotopic element is integral differential operator instead of Planck's constant. The rest of the iso-Schrödinger representation is elementary. You only bring to your attention to that here the eigenvalue or iso-eigenvalue. But iso-eigenvalue or eigenvalue multiplied by iso unit. The star means multiplication by the isotopic element. They are opposite to each other. They cancel, so at the end you get an ordinary number. That's why I believe that hadronic mechanics, the test of hadronic mechanics, experimental tests are indeed valid. Otherwise, I would say no. Then this is Professor Garrett. This is matrix mixed. Here is Hilbert spaces and so on, but here a totally matrix formulation and the isotopy of the Schrödinger representation, which you know from the first lecture. And this is the infinitesimal part, and this is the the integrated part, where you can see the germ of a bimodular structure, because you have an axial from the right and an axial from the left. However, they are equivalent. So this means, careful, that the totality I have said in this lecture is that is only applicable to systems that they are reversible over time. It's a duty to do serious science. Whenever we come up with a theory, we got to identify the limitation. The theory without limitation never existed, will never exist. In this case, we cannot, with this, whatever I said, we cannot apply what I said directly to nuclear fusion because they are irreversible. So in the isotopos, quantum mechanics is reversible, isomathematics is reversible, isomechanics. So it represents a nucleus, a stable, isolated nucleus whose time reversal image verifies causality. And so therefore, we can represent it with internal. Ladies and gentlemen, I believe this is all I would like to say. And I beg you for critical comment, please.
Thank you very much. We have run over time a little bit, but I see Professor Słowczyk has a question.
I just have a simple question. We've talked about how iso-Lie algebras arrive. What about the corresponding iso-Lie groups by just taking the exponential of an iso element?
This is one-dimensional iso-Lie group, Lie-isotopic group. It is here. This is it. It verifies all the axioms of a Lie group. Again, you can write this. You can write the Lie-isotopic group with same symbols of a Lie group, and you get the same thing. You get only the definition is different. And you see here, you can remove the star in the product, and you have A multiplied by H, and you can say, okay, but the multiplication has freedom. So one is the high school multiplication, or no, the one is the one with the T in the middle. But the equation you can formulate with the same symbol.
Okay, very interesting. That last equation at the bottom is also it's just like on both sides you're operating by e to the h and so on. That's like we do with spinors in geometric algebra, two-sided representation of a rotation.
It's a bimodular. Be careful that here this is all in according to isomathematics. The product isotopic, and let me see if I can go quickly back. See the iso unit. The exponential is isotopic. This is calculated with the infinite series for Poincaré-Birkowitz the theorem. So it has you see here there is an iso unit. So that's why when you go here, sorry. When you go here, you see the star disappear. Which this means that the T has been cancelled because of the presence of the isotopic element, which is the inverse, and that's why this is reduced. This is projected in our space. But the correct formulation is the one on the left, because everything is isotopic. Has to be. Also notice that there is no isotopic element in the exponent. It emerges by the definition of the iso exponent. It becomes mandatory, comes out automatically.
Okay.
This means that you're talking about, you see here, this means that this Lie-isotopic group, even the axiom of the Lie group are verified. It is extremely nonlinear in the wave function. Remember the arbitrary functional dependence on T. So the general presentation of Lie theory that is solely applicable for linear system should be clarified that it's solely applicable to linear system when formulated with 20th century applied mathematics over a conventional numeric field, because it's the same axiom are formulated according to isomathematics on an iso field. And yes, nonlinearity. That's why we built the whole thing to get represent the nonlinear. And the embedding of nonlinear interaction in the Lie theory is crucial to get the symmetry, in our case, the isosymmetry, that if you are interested, I can outline it for you sometime in the future.
Thank you very much.
Yeah, I think we have to stop at this point, but well, one more question, Jesus.
Please, only one elementary question. You can have one product between one iso number and one elementary number?
Could you please, Professor, could you please repeat the question? I want to be sure.
Yes. If we can have products between one iso number and one elementary number.
No, it will be inconsistent. It will create inconsistencies. It will be exiting, mixing mathematics and isomathematics but I have to be to the best of my knowledge. I could. This is a degree of freedom that has not been investigated to my knowledge. You may be dealing with a new degree of freedom. For instance, another aspect that has not been investigated, if we do the isotopic lifting of the sum and related additive unit, but not of the product, do we have compatibility? I don't know. I do not know the answer. Maybe yes, maybe no. I know that we have compatibility if we lift the product and maintain the sum, but not otherwise. I'm not sure. But your point, yes, it could be. You can introduce it. You can introduce a new iso field, which is the Kronecker product, not the iso product. We have a Kronecker product of an iso field multiplied by an ordinary field. So your theory will be defined on that new field, and not on an iso field alone. And mathematically, I think will be consistent. I see no reason why you should not. So you have a point, Professor Cruz. So these are fields that have been investigated very, and there is so much to be done.
Okay, thank you.
Thank you for your question. Thank you.
Can I, just to follow up on that, I just highlight one expression on this slide. Here, is this an example of an operation between a elementary number and an iso field?
Yeah.
Well, you mean the mapping, what I call mapping, so to say, which is not necessarily.
Well, E without the hat is an elementary number.
Yes, that is correct.
But the bracket there has hats on the side.
Yes.
Right. So that represents an iso field.
Number. That is correct. Yeah.
But
So
then the question, Jesus' question, is about the meaning of that operation, multiplying an iso field by an elementary number.
Yes.
Yes. Now let me tell you what we do in, which is not necessarily an answer to your question, but what we do essentially, the experiments are done in an ordinary space, say the ordinary Euclidean space, defined over an ordinary real numbers. So this is the equation that we accept from the experiment. And basically, but the point is this, that we don't do we don't test, we cannot test. I do not know how to do an experimental test of the iso-Heisenberg equation defined on the iso-Hilbert space. I do not know how to do it because it's too abstract. So what we do in the actual experimental verification, we test the projection of that Schrödinger equation in the conventional Hilbert space. In that projection, you only see E multiplied by the wave function. You don't see this. This disappears because they cancel out. So this will be the physical answer. However, this from a mathematical viewpoint, oh my God, the Professor Cruz certainly valid. You can formulate an intermediate step to define the iso-Hilbert space on the product of an iso number multiplied an ordinary number. You will get a consistent theory, I believe. Yes.
Okay, I think we need to stop at this point, and I appreciate your persistence, Dr. Santilli. You've spoken for a long time.
Half a century. It lasted half a century, this adventure, but it was intriguing indeed. It was mentally stimulating. And if you have
so we will skip next week. We'll take a break. Jesus, you will be presenting in 2 weeks' time. Is that correct?
Yes, that's right.
I'll be back.
Okay.
Okay.
Perfect.
Thank
Bye
you
for
for
now.
your patience. Thank you for your
Thank you.
patience. Appreciate it. Thank you. Have a good day.
Yeah, you too.
Bye.
I'll mail to all of you. I'll mail the PowerPoint.
Thank you very
Yes,
much.
please do that.
Thank you very much, Dr. Santilli.
Thank you for
I was looking for for your articles and the work of non-associative algebra by Dr. Jaak Lichmos.
Yes.
Do you remember him? Yes. And yes, it was difficult to understand, but now it is something more or less clear, more or less.
Please.
I will send you my book. I haven't sent that to you, I believe. I will send that to you now.
But,
Okay,
please,
thank you very much.
please, those concepts they're not that easy. If you have any question, please send it to me. We can have a session, a Zoom session of the two of us and discuss. I am available. The only thing I do now, I'm terminated all industrial applications. So the only I do is study these things and try to.
I'd love to come down there and visit you. My sister is living in Florida, not far away, and one of the islands down there. So I would like to visit you sometime down there.
I'd love to see you, and that absolutely would be the weather. Where are you? May I ask which part of where are you located in?
I'm in South Carolina.
We are in South Carolina. It's already the chilly there now. Here the weather is nice in Florida, and so
Exactly.
very well. Well, gentlemen, thank you. And I remain available for any question you have in mind. And please contact me. I'm available for the directed Zoom session because with email sometimes it takes too much. They're too slow. It takes too much to discuss. It's very difficult. While discussing, in person in a Zoom session is much more
That's true.
efficient. Absolutely, yes.
Okay, very good.
Well, then thank you. And
See you in 2 weeks' time.
Appreciated your this opportunity, Dr. Pace. Thank you.
Bye for now, everyone.
Bye, everybody.
Bye.